distinguished chairman and the auditory, I express my gratitude to the organizers of this workshop and for the opportunity and the pleasure to be present here today. So I'm going to present you some of our, I would say, one of our most valuable experiences in retrofitting historical buildings, which is seismic retrofitting one of the parliament building of the Republic of North Macedonia, necessity, solution, and construction. So probably you are familiar with the parliament building. So there was a project for enlargement of the building, another story, and adaptation of the parliament building. So we had three challenges here within this project. Definition of possibilities and conditions. As you know, this building is a building of very high importance for the country. So definition for possibilities and conditions for its repair and strengthening should be taken care very seriously. Estimation of existing stabilities, also a big challenge because it is a complex procedure, specific, and also a responsible task. And finally, strengthening of the main structural system. Actually, why strengthening of the structural system, since the historical building, plain masonry, built from 1936 till 1939, before any seismic code has been adopted within the country and further in Europe. So some knowledge from the technical, written, and photo documentation. So it looked from above, it pretty much looks like an irregular pentagon. So some of the history of the construction I already mentioned. So from 1936 till 1939, original structure of the Pentagon, which has been constructed by brick masonry walls in both directions, and then also the main hall that you can see here with the green line, constructed by reinforced concrete as a reinforced concrete frame structures. From 1954, the first enlargement, or the second hall, also constructed as a reinforced concrete frame structure at the time. And Crystal Hall, basically replacement of the existing masonry with reinforced concrete columns and steel beams. In 1963, post-earthquake repair. So as you have been aware, so in 1963 we had a catastrophic earthquake in Skopje, a lot of demolished buildings, a lot of casualties, and homeless people. So that was the starting point or the trigger for the creation of the European Society of Earthquake Engineering. So 1963, the post-earthquake repair, which included injection, rebuilding of collapsed part, grouting of partition walls, pre-stressing of walls, consolidation of parapets, etc. From 1964 till 1965, a second adaptation, strengthening of the halls by reinforced concrete belt courses. And then 1967, second enlargement, the Hall 3 and 4, constructed as a reinforced concrete frame structure. From 1996, the reconstruction of northeast angle, but implementation of the reinforced concrete elements, and finally 2005, we received the project for enlargement, building of another story over the Pentagon, and adaptation. All of it around 3,600 square meters of enlargement. So the main structural system of the Pentagon, as I mentioned before, it has been constructed as a massive brick walls combined with concrete belt courses and columns. Approximate analysis of repaired building show that the global safety coefficient is 2 for coefficient of seismicity equal to 0.12, which was pretty much satisfactory at the time of, according to the old codes from 1964. According to the technical condition for the building of another story, it has been reported that the structure is constructed of massive brick wall framed with reinforced concrete horizontal and vertical belt courses system known as confined masonry, which is significantly different from plain masonry. Also, that there is a possibility for building another story with low life loads, but after additional investigation. So all of this resulted in ambitions for making a project for enlargement, building of another story, and adaptation from 2005. So what would be the main reason of the technical investigation that we perform? Precise definition of the main structural system, since there is no crucial difference between, because there is a crucial difference between the plain and confined masonry. Identification of reinforced concrete vertical belt courses and compare with the code requirements for confined masonry. So actually we assumed that there are some reinforced concrete vertical belt courses, but we were not sure. We had to confirm it. The chosen methodology was a selection of the Southwest unit as a representative structural unit. And then we performed the detailed non-destructive testing of Southwest unit using some of the testing equipment that we purchased at the time, precisely ProSig Profometer for defining the presence of reinforcing bar in structures, and confirmation of finding by minimum number of destructive testing. So we performed some testings, and what we found is some places that were looking like that they looked like columns, and then we had to approve that we are dealing with reinforced concrete columns. However, some of the elements that look like reinforced concrete columns were really a reinforced concrete columns, but some of them were just masonry columns. And also some places that we expected that we may find reinforced concrete columns or belt courses were just masonry, were constructed of masonry. So actually what we achieved is locating the identification and locating the reinforced concrete vertical elements in selected structural units. So in red dots, you could see the places where reinforced concrete columns or belt courses were identified. So it is not far from the conclusion that identification of these elements is the structure with the identified reinforced concrete belt courses within these places is far from confined masonry. So what we needed to do, as I mentioned before, is intensity, placement, and quality of building materials. That we concluded that the building materials are not sufficient for the structure to be called confined masonry, according to the requirements in valid technical regulations. So these are some parts of the technical regulation that define confined masonry. all corners and intersection of the walls must have reinforced belt courses. All three ends of walls with wall thickness of 19 centimeters and higher have to have reinforced concrete vertical belt courses, and also the vertical belt courses should be at the maximum distance of 5 meters one from another. So some words about the global seismic safety that we concluded around 2 according to the code from 1965, which takes the base shear coefficient of 0.12, which means like 12% of the total mass is applied as a seismic force. That is the maximum force that the structure is capable of sustaining. But less than 1, we're talking about the global seismic safety. So less than 1, according to the technical regulations that now are on power from 1961, which require the base shear coefficient for these structures to be 0.3. So we have like higher than a double need for sustaining seismic force. So the general conclusions from the investigation is that the existing structural system has unknown bearing and deformability capacity. What we could assume and to be sure about it, that the bearing and deformability capacity of the structure was not satisfactory or not enough to sustain the forces required by the present code. A little bit about the conditions for building another story. So detailed analysis of the seismic stability was required, and then structural strengthening allowed number of stories, and the number of stories is also limited according to the code, especially in plain masonry. And dynamic analysis for expected earthquakes as a structure of first category and the structure of high importance. And finally, additional necessary investigation. So the performed additional investigation were, first of all, site inspection. So definition of geotechnical and geodynamical models of the site, definition of seismic parameters for evaluation of seismic stability of the existing structure, or calculation of estimation of the seismic hazard on the micro level. And then it has been performed by the Department for Geotechnical and Geotechnics and Spatial Structure within our institute. So we defined the local hazard, we defined the local earthquake response spectra that we need to work with, and specific earthquakes that we have in our database that have sustainable spectral features that can cover our requirements. So in the performed additional investigation, as I mentioned before, definition of geotechnical and geodynamical models on the site, seismic parameters for evaluation of seismic stability of existing structures, and investigation of the main dynamic characteristics. So we performed that with our equipment for on-site testings, for in-situ testings, for ambient vibration records, and what we gained from those records is the dynamic features or dynamic parameters of the building on site, not analytically, but on site. Also, some investigations of the built-in materials. So some sample of the building materials were removed and then tested. Additional technical measurements and in situ investigations, like searching for reinforcing bars, searching for some kind of features that we could use in our analysis. Methodology for analytical investigations. So we have 3 general state: existing, with additional story, and strengthening. So all of this 3 general states. So all of these 3 states were subject of our analysis. Then safety definition of safety criteria. What we actually expect and what we want to achieve with our approach for strengthening of the structure, and then analysis of structural element up to its limit state. Analysis on bearing and deformability capacity. And then analysis of seismic behavior for defined seismic parameters. As I mentioned before, we used several pre-recorded earthquakes that we used as an input into our time history, nonlinear time history analysis of the building. And finally, analysis of variant solutions from the aspect of stability, economy, and possibility for the construction. So the existing state, what we say about the existing state. So unstrengthened state with 4 lumped masses on the levels of their story level. The second with additional story, but still not strengthened. So 5th mass as an additional story, because the project for upgrading required additional story. And finally, strengthened state and with additional story as a final product of the reconstruction and upgrading of the building. So we defined the safety criteria. So 3 levels of safety criteria: elastic behavior, beginning of non-linearity, and then ductility of the material less than 1.5 for 100 years return period. The local site investigation results suggested to go with maximum ground acceleration of 0.27 G. The second level is already a non-linear but limited non-linear behavior with ductility between 0.5 and 2.5, and for earthquakes with a return period of 475 years, a period that is commonly used as a design, as a period of the design earthquakes. And finally, a level 3, deep, which could take into account deep non-linearity but non-disturbed stability. So some substantial damages are allowed on the structures, but still stability would have to remain. So it required 2.5 up from 2.5 up to 3.5 ductility for earthquakes with return period of 950 years and maximum ground acceleration of 0.42 G. So actually some definition of our terms: bearing capacity and deformability capacity. So the bearing capacity, it's basically ultimate story transversal force compared with the equivalent seismic force gives the safety factor against failure. And deformability capacity is the maximum ductility as a relationship between maximum deformation and deformation at at the yield point. With a nonlinear analysis, we have the same parameter like masses, input parameters, masses concentrate, which are considered as concentrated at the floor levels, and the hysteretic models of the material behavior by submitting an elastoplastic characteristic of separate walls. So analysis of the existing state, we have all the sections here, all the units of the building. What we need input shear base of 0.3, which means 30% of the total weight of the structure as a result of its structural system and importance class. We defined physical parameters like elasticity modulus for the masonry that has been used as a structural material, and then the compression strength, tension strength, and the specific density of the used material. So we defined the quality of the concrete from 16 to 23 megapascals, which is below the nowadays standard concrete quality, and reinforcement with a yield strength of 240 megapascal, which is more than a double of less than the reinforcement used nowadays. What we earned as an output, the bearing capacity for the sections from section 1 to section 7 is 6 up to 18% of their total weight, and required is 30%, so much less than the required. Ductility capacity from 1.4 to 2.1, and it is about and it is required up to 3.5, so much less. The final conclusion after the analysis of the present state is that the necessity for structural strengthening is analytically approved. This structure could be marked as a structure that does not require the safety criteria that it needs to require. So a little bit about the approach of the analysis of the masonry walls. So we had three approaches: analyzing separate walls, analyze as meritory, analyzes adjoining walls as a control of the previous analysis, and the whole pentagon as a one single unit without any expansion joint, as without dilatation, as a final check. So we decided to analyze it as a separate walls as most conservative, but like but the solution that is closest to the real situation. So these are some results from our analysis. So you can see here the bearing capacity in both direction of the chosen unit of all 7 units, required ductility, and calculated analytically approved ductility. So here you can see that the bearing capacity is far less than the required one, and the ductility and the ductility capacity is much less than the required ductility capacity. So we had to go further for technical solutions for structural strengthening, which could be based on required additional strength and deformability. Demand versus existing. Sorry? Okay, thank you. And then requirement in technical regulations and minimum intervention for optimal results. Some limitations were requirements as a historical building under protection by the law for cultural heritage. possibilities for implementation of new reinforced concrete elements into historical buildings. Avoiding intervention in areas appointed by the investor, like specific areas, expensive interior with high value or significance, or maybe area with containing some classified architectural information. And then continuous functioning of the parliament during realization of the strengthening. So this was absolute condition. The parliament needed to be operational and functional parallel with the works for repair and strengthening. The concepts for strengthening various solutions from the aspect of stability, economy, and possibility for construction. And then selection of the most appropriate solution using classical methods and elements using the same building material as the existing one. So the technical, some of the consisting of the technical solutions, connecting of longitudinal and transferred elements with horizontal reinforced concrete belt courses above the top story and the horizontal steel ties at the floor levels. Then implementation of reinforced concrete jacketing on part of the bearing walls founded by enlarging of existing foundation. So actually the reinforced concrete jacketing walls was the dominant method that we used here. Substitute of the part of the population of the partition wall or implementation of new reinforced concrete shear walls connected with the horizontal ties and founded on the new foundations. So implementation of elements that didn't exist before, reinforced concrete shear walls as a new elements in the building. Increasing of the dimensions and reinforcement of the existing reinforced concrete columns founded by enlarging of the existing columns. Then injection of eventual cracks in the concrete and brick masonry walls, additional in situ technical solutions during realization process, and finally, So finally, you can see here, if you can spot this pink zones, these purple zones. So these purple zones are basically the elements of for strengthening the structure that were implemented, that were designed and needed to be implemented in the building. So actually here is one part zoomed, and you can see here the rate of implementing element for structural strengthening. So every dark or black lines are basically reinforced concrete jackets or reinforced concrete shear walls that were implemented like a new elements for the structure to sustain the required seismic force. So some words about strengthening state. So we analyzed the present state or state at present at the time before strengthening. So we concluded that it has been far from satisfying. But analysis of the strengthening state. So the masses were redefined. The mechanical characteristics were redefined, and now the input has been a little bit decreased since we are not dealing with pure plain masonry anymore, but we are dealing with strengthened masonry, confined masonry, or masonry that has been strengthened with jackets. So we expect for that kind of masonry to have a higher ductility. So if we have a higher ductility, then we can increase the input, input elastic, the input seismic force for the for elastic design. So the new reinforced concrete elements were designed and constructed by stronger concrete with higher quality, and also reinforcement with a higher tension strength. Here, as a comparison, you can see some results that we obtained analytically. So bearing capacity, required ductility, and ductility capacity. So actually, the bearing capacity and the required ductility are here. The bearing capacity has been increased, and as I mentioned before, the demand has been decreased as a result of higher ductility with the new elements implemented as strengthening elements. So here, the bearing capacity, you can compare achieved and ductility capacity. So they are quite higher than the demanding. So here you can see some charts, some diagrams of energy dissipation capacity. So actually displacement versus seismic shear force. So you can see the substantial difference in the behavior of the structure before strengthening and after strengthening. So actually the compression strength and ductility was similar, but the compression strength and energy dissipation capacity was significantly improved. So here I have list of all the sections. So actually all the sections in both directions are displayed here. So we had the most significant change we had in section 6. You can see the white zone comparing to the blue zone, how bigger it is. And finally, the 7th section. So all the section demonstrated much better performance. So optimization of strength, bearing, and deformability capacity was achieved. Improved structural stability for expected seismic effects. And the reconstruction starts in April 2010 with section 7. So the parliament was continuously functioning functioning for its main purpose. And it was also supervised by EASY's team that encompassed detailed inspection of the geometry of individual units and every single strengthening element. Then direction of activities and prescribing of order regime and technology of incorporation of strengthening. Elaboration of variant solutions for modification of individual elements due to newly created and limiting conditions of performance of the works on field. Definitions of social solutions based on the control, computation, and the engineering knowledge harmonized with the possibilities of the contractor and the conditions for performance of the work. And finally, definition of technical solutions for strengthening of new positions that arose from the necessity of structural interventions, especially for the third and the first section after beginning of the works. So section 1, 2, 3, and 7 and part of section 6 were finished until September 2011. So realization of the strengthening process. Here you can see some details, some photo evidence and photo documentations of the construction works performed. So here how it looked, this part before jacketing, parts between the windows that we were expecting to find reinforcing bars and where we didn't find any reinforcing bars. Here's some also some details of strengthening of one wall, and here's some reinforcement that before concrete casting. These are some details that we use to connect to bars. And here's the same wall that we expected to find bars, but we didn't. So we implanted. So we actually constructed a reinforced concrete jacket with bars. So here a closer view. Some ties for confining the strengthening elements. Also, some parts that were constructed as reinforced concrete were found damaged, so they were repaired later. Enlargement of the foundation and addition of foundation beams, additional foundation beams. Also, enlargement of reinforced concrete foundations at section 3, if I remember correctly. Strengthening of the reinforced concrete column with extra reinforcement, because the old reinforcement were corroded. Some details for anchorage inside the new casted concrete. And finally, a new reinforced concrete jacket. Some mounting of reinforcement and getting it ready for jacketing. So this was the plain masonry wall. Now it would be jacketed, and some anchors that are used to interconnect the new jacket with the old masonry wall. And these are some details from the patio. Looked from the patio. These are columns, reinforced concrete, but above them there was only a masonry structure. These are some details of the construction work at the field. Jacketing, and now as at the end, so we have strengthening structures, we have upgraded structure with additional story level and also a domes, and finally in 2016 we had earthquake as a test for the new